In this video, we're going to model a fuselage of an airplane as a thin-walled cylindrical pressure vessel. And in order to figure out the axial stresses that are going to be present in this fuselage, we need to know what the pressure inside the fuselage might be versus the pressure surrounding the fuselage. So when you're on the ground in an airplane and the doors are open, it's 1 atmosphere, 101.3 kilopascals inside the fuselage, and it's also about that outside the fuselage. And if you were to leave the doors open and go up 10,000 meters, there would be no pressure differential as well. But you'd have a different problem in that your passengers would be extremely uncomfortable and not be able to breathe unless they had some oxygen being given to them in a mask. So what we do is we pressurize the cabin, and that means that there's going to be an internal pressure that is similar to what you would have on the ground. Maybe it's a little bit less, but close to 1 atmosphere. And then there's the surrounding pressure outside the plane that is much less. So the first part of this question is to figure out what the gauge pressure is. And this gauge pressure is going to be the 1 atmosphere of pressure that you're trying to keep inside the fuselage minus the pressure of the outside air surrounding the fuselage. And to calculate this outside pressure, this is essentially an absolute pressure. What you see is this equation 101 e to the negative 1.12 times 10 to the minus 4 times h, where h is in meters. Now, you could argue this may not be the most accurate constant here. It depends on temperature, okay, and it might be a little bit low. But for this problem, we're going to go ahead and use this exponent. Maybe minus 1.2 would be more appropriate, like at 15 degrees Celsius. And you can look online for calculators that go through these calculations. So let's go ahead and bring up Colab or Python to be able to do this numerical calculation. So we're going to come over here and we're going to bring up Google Colab. And the formula that we really want is right up here. Okay, let's go ahead and import NumPy as MP. Okay, Control Enter. Maybe I'll make it a little bit bigger so that you can see. I'll do a little more coding. So let's call this. We'll do a few different things. We'll do H is equal to 10,000, and we'll say that's meters. We'll go ahead and we'll calculate the P outside. So P out at 10,000 meters. So that's going to be 101 E. So 101 times exponent minus 1.12 times 10 to the minus 4. Whoops, I got to do it like that. Okay. And then times H. Okay. And that should do it. And that's going to give it to us in kilopascals. All right, so we'll do that, kilopascals. But maybe we want to put it into pascals, so we'll do times 1,000, and so that will give us in units of pascals. P in, that's the internal one. That's just 1 atmosphere. All right, so 1 atmosphere, though, you don't really want to type it out like that. 1 atmosphere is 101.3 E3, and that will give us the internal pressure inside the fuselage. Okay, so these are both absolute pressures. So the delta P is going to be, yes, it's actually not P out minus P in. It's going to be P in. Let's see, does it pick it up? Yeah, it did. Wow, look, artificial intelligence. Okay, so we're going to go ahead and let's print some things out. So we'll print, because we might be interested in knowing what the the absolute pressure is? Yeah, okay, so that will do that. Whoa, it did a bunch of things here. Let's see. All right. Yeah, that's so we can do this. I'm gonna modify things a little bit, do some rounding, and I'm gonna actually multiply by 1 e to the minus 3. Okay. And that will give it to us in kilopascals. All right, but P out is going to be uh, keeping it uh, in terms of pascals for the calculations. This one, sure, we can spit this out, but it's not. It's really pretty trivial because it's whoa. Now I can't see anything because it's really just oh my goodness. I guess it's very hard when here we go. I don't need so we'll do times 1 e to the minus 3, and that will be kilopascals. And then sure we can get the delta P out of here too. So MP round. Wow, I'm having trouble with my period. I don't know why it's that point is not coming out. All right, but we're going to also multiply by 1 e to the minus 3, and we can do sure to 2 decimal places. And we'll say this is KPA, and then like that. It didn't like, yeah, because it's missing that. Okay, I think it's happy now. Let's see what we get. So we control enter this. Okay, I made a mistake. What did I do? Oh yeah, okay, so this has to be NP, like that, exponent. Okay, now it has some numbers. Okay, so the outside absolute pressure is about 33 kilopascals. The inside absolute pressure is 1 atmosphere, which is what we specified. So it's just spitting out the same exact thing. And the delta P, the gauge pressure, is about 68 kilopascals. So you may think this is, it's well, the pressure is lower outside. So why is now the gauge pressure higher? Why do we have like this? Why is it under tension now? Well, it's because these two sides are sealed from each other, right? The door is closed. And there's going to be now a pressure difference. There's going to be a pressure difference between the inside and the outside. Okay, so that's the delta P. The next part of the problem is to figure out what the, well, let's just go back to it. The next part is to figure out what the hoop stress and what the axial stress in this fuselage are going to be. And to do this, we're given that the radius of the fuselage is 2.5 meters. That's, not that bad an estimate if you think about, all right, I'm sitting in the airplane and how tall it is and everything else. And there's some luggage underneath, some stuff air above, the space above. So R is equal to 2.5 meters. The thickness is only going to be 1 millimeter. That's pretty thin, okay? But that's what we're going to use for now. And we're going to have the calculation of the tensile, hoop, and axial stresses. We're going to use the change in pressure. And the formula for hoop stress is the sigma theta is equal to delta P R over T. And the longitudinal axial stress is going to be half of that value. Okay, so now let's go ahead and plug in that delta P that we calculated prior. So for this, we could continue, or we'll just add some more code down here, another cell. So we have the hoop stress, so we'll call it sigma H is going to be equal to the delta P times an R divided by T. And this will give us units of pascals. But what are R and T? Well, we said that R was 2.5 meters, so we'll just put it like that. And the T was 1 millimeter, so it's probably better to do 1 times 1e. I mean, you can do a different way. You could just 1 like that, okay? But that will convert the millimeters to meters. And so now we can calculate sigma h, or the hoop stress. And we can also calculate the axial stress. So we'll call this sigma axial. That's fine. All right, and that's going to be the delta P. Oh boy, okay. Sure, that's fine. P times R divided by 2 times T. I really didn't have to do this. I could have just taken the sigma H and divided by 2, but I'm going ahead and I'm just rewriting the equation out. Um, and does this all look good? Yeah. So let's see what we get. So it thinks it's know what I want. It thinks I know what I want it to do. Let's see if it's true. Sigma h is equal to this, yeah, y times 1 e to the minus 6, fine. That will give us a result in megapascals, okay? And sigma axial, yeah, that will also give us a result in megapascals. That looks pretty good. Let's see what we get. And when we come down, all right, we get 171 megapascals for the hoop stress, and we get a value of half of that for the axial stress. Once again, we realize that this calculation of these axial stresses is going to be dependent on a ratio of R and T. And typically, like we've said in class, that R is, a factor of 10 or more that of T. So even though we're dealing with, kind of modest pressures, less than an atmosphere for the pressure difference, because this ratio of the radius and the thickness is so high, we end up getting pretty significant stresses in a material. So, a material like carbon fiber or aluminum can easily be tuned to have a yield stress greater than 170 megapascals. Uh, but you could see that just small changes in the thickness, in the in the in the calculation of the pressure, right? They could have pretty large impacts on the stress that the material might be experiencing. At any rate, I hope you found this example helpful, and thank you for watching.